So this evening I want to talk about our second different type of advanced data structure, and those are graphs. And we'll take a look at graphs this evening because they're important data structure. And we'll start with a little bit of motivation, and this has to do with the Königsberg Bridge problem. Königsberg was a German city, but it's now in the Russian exclave area and is known as Kaliningrad. So classically, the river Pregel flows around this island in Nightpop and then divides into two different branches. And there were seven different bridges in the city of Königsberg. And so the mathematician Euler was wondering, hey, is it possible that I could start out at, say, bridge C, walk over all seven bridges, and get back to where I started without walking over the same bridge twice? And it turns out that you can't do that because what he did was, after probably trying to walk it, or at least I would try to walk it, he represented the problem as a graph and determined that you couldn't do so because what you need here is an Euler circuit. And a connected multigraph with at least two vertices has an Euler circuit if and only if each of the vertices has an even degree. And so you can see D has an odd degree of 3, A has a odd degree of 5. So basically, there aren't any of these that really have an even degree. So if all of them had an even degree, then you would be able to do it. But you can't solve this particular problem unless you swim across the river or get creative in some different way. So this is an application of graphs, and there are a lot of different applications of graphs that you find in computer science and mathematics. One is finding optimal layout for circuit board components. Another is route maps for trains and planes. Relationships between people, seeing where there are connections between them. Co-author graphs, etc., organic compounds and molecule diagrams. We'll see an example of those. Connections between different network components, PERT charts and project management, and there's a whole heck of a lot of other ones. So the graphs are a very important data structure for modeling real-world phenomena, and we're going to see how we can produce graphs in C++. So there are a bunch of definitions, and one of the frustrating things with graphs is there's really no standard set of definitions in the mathematical literature, and a lot of it depends on which textbook you're using. But let's go over some definitions regardless and see what some of them are. So a graph consists of a set of vertices, V, whose members are called vertices, together with a set E of pairs of distinct vertices, and those are the edges. If an edge connects V and W, then V and W are said to lie on E, and E is said to be incident with V and W. If the pairs are unordered, then it's called an undirected graph. If the pairs are ordered, that means I can go from A to B, but maybe not back. Then that's called a directed graph. And the term directed graph is often shortened to digraph. And the unqualified term graph usually means an undirected graph, but not always. Again, the notation and the definitions are not completely standardized. So, make sure you know what definitions you're using in the text or the course that you're working with graphs in. Two vertices are called adjacent if there's an edge from the first to the second, and the valence of a vertex is the number of edges on which it lies. So the number of vertices that are adjacent to it. A path is a sequence of distinct vertices, each adjacent to the next, that allows you to go from one location in the graph to another. And a cycle is a path that contains at least three vertices, such that the last vertex on the path is adjacent to the first. In a directed graph, a path or cycle means always moving in the direction indicated by the arrows. So you can't imagine that you can go the opposite way down a one-way street. Such a path is called a directed path. A graph is connected if there's a path from any vertex to any other vertex, and a free tree is defined as a connected undirected graph that doesn't have any cycles in it. A directed graph is called strongly connected if there's a directed path from any vertex to any other vertex, and if we imagine that the graph is no longer connected, the resulting undirected graph is connected, then we call that directed graph weakly connected. So let's take a look at some examples of graphs, and we'll start with Hawaiian Airlines. And boy, you have no idea how small the mainland is until you see it on a map next to Hawaii. Just kidding, this one's not to scale, but we can see where Hawaiian Airlines flies. So, if we wanted to imagine that we wanted to go from Hilo to Seattle, then we would go from Hilo to Oahu and then up to Seattle. Or there is also a flight from Hilo to Kahului, which could take us on to Seattle. So, we could see several different routes to get there. Another example of a directed graph is molecules. This is the caffeine molecule. I think the textbook has benzene in it, which is not the most exciting molecule. I much more prefer caffeine. But here we can see the strong and weak type of bonds between the different molecules. A message transmission in a computer network. Here we can see that we can send a message to either B or C as a node within that network. B can go to D and D can go back to B. But after you leave A, you can't get back to B. So that's an example of a directed graph. These are connected graphs. So on these, they're undirected graphs. In the first one, we can get from 1 to any other vertex. It could be a path from 1 to 2 over to 4 and then to 3. And if we wanted to find a cycle within that graph, we could go 1 to 2 to 4 to 3 and then back to 1, and that would be a cycle. This one's a disconnected graph. If you're in 3, you can't get to the rest of the graph, and if you're in 1, 2, or 4, you can't get to 3. So that's that old New Hampshire saying, you can't get there from here. But this one is a free tree, so there are no cycles in this one. And this is an example of a directed cycle in the graph. So we can start here, move over here, down here, over to the right, and back up to the upper left. This is a strongly connected directed graph. Basically, you can start in any node and get to any other node. This one is weakly connected. Basically, there's a problem if you start in the lower right, because you basically end up in that cycle that covers these 3, 1, 2, 3. And you can't get out of that cycle to visit the upper 2 and the upper right. So, but if you imagine that you suppress the direction of the arrows, then that becomes a strongly connected undirected graph, and so this one ends up being weakly connected. So when we're putting graphs together in computers, there are a couple different ways to do it, and particularly in high-level programming languages such as C++, we can represent graphs in a couple different ways. One of them is an adjacency matrix, and the other is an adjacency set or list. And so we need to store these graphs in computer memory, and there are a couple different ways to do it. Adjacency matrices are probably my favorite way to do it, even though they're in some ways less efficient. Basically, we build a table that indicates each pair of vertices, one going down the rows and one going across the columns, and we have it as a two-dimensional array of Boolean values, and it's true if there's a connection between the two vertices, and it's false otherwise. So this one's fairly easy to understand, and we can also modify for networks. We could change it to be int, and then put the weights into that two-dimensional array. So we can add weights onto the edges as well, which will be important a little bit later on. Adjacency list or set implementation, basically each node gets a list that contains the other nodes to which it's connected. So each node has two components, such as a vertex and a link, or a set of links to the other node. So here's our directed graph over here on the left. Here's how we would represent it using an adjacency list or adjacency set. Vertex 0 is connected to 1 and 2. Vertex 1 is connected to 2 and 3. Vertex 2 is not connected to anything. It's a null pointer. Vertex 3 is connected to 0, 1, and 2. And the adjacency table, basically here we can see that 0 is connected to 1 and 2. So I can go from 0 to 1, I can go from 0 to 2. From 1, I can go to 2, and I can go to 3. From 2, I can't go anywhere. And from 3, I can go to 0, 1, or 2. So that's how we would represent this graph using either an adjacency list or set, and how we would represent it using an adjacency table. Some of the operations that we need to do on graphs. One, we need to create the graph. 2, be able to clear it out, make it empty. We need to do that with a lot of our different data structures. Determine whether or not the graph is empty. Traverse it, and then print the graph. So graph traversal, this is pretty much, there are a couple different ways to do it. One is as a depth-first recursive algorithm. And basically, depth first is roughly analogous to pre-ordered traversal of an ordered tree. So you imagine that we start the traversal and we visit vertex V, and W1 through WK are the adjacent matrices, or adjacent vertexes to V. So we visit W1 and then keep visiting the neighbors of W1 and keep W2 through WK waiting. After visiting W1, we traverse all the vertices to which it's adjacent, then do the same for W2, and then finally we get to finish off at WK. So if we start with this graph, we start at 0, and then we visit 1, which is the first vertex that's adjacent to it, and store 4 and 8 for later. Then we visit 2, then we visit 3. Okay, we visited all the way down there, and then we go back to start, we visit 4. Okay, what's adjacent to 4? 5. What's adjacent to 5? 6 and 7. Okay, we're done. We can't visit any further. We go back up to 0, and we visit the last one that we stored at the very beginning, which is number 8. So breadth first traversal is roughly analogous to level by level. Okay, so that's depth first, and then breadth first is roughly analogous to level by level traversal of an ordered tree. If the traversal is just visited vertex X, then it visits all the vertices that are adjacent to V. So it'll produce a slightly different order with our graph. And so here we start at 0, then we visit 1, 2, and 3. Those are all the ones that are 1 away from 0. Then we visit 4 and 5. Those are both 2 away from 0, 6 and then 7 are 3 away, and then finally we visit 8, which is 4 away from that. So that's a breadth first traversal of that graph. So the depth first algorithm, one of the things you'll notice when looking at this one is that it's actually a recursive algorithm, and we can basically write this very quickly as a recursive algorithm. The auxiliary function does the depth first traversal for us. And then the breadth first algorithm, which is not written as a recursive algorithm here, but uses a queue to store those in. So it's a first in, first out, whereas the depth first is last in, first out, or a stack type of structure. And you could write the depth first non-recursive and make use of a stack, but it's probably easier to write it as recursive. So we'll get a chance to look at these during the lab, so don't worry too much about the details of the code, but worry how these algorithms work. Anyway, that's what I have for today. Thanks so much for watching.